So the next topic that we'll discuss are fiber optic sensors. Right, so optical fibers and devices made out of optical fibers are also used as sensors, basically for measurement of various physical and chemical parameters or variables in the environment that is useful for some particular application, right? So, for example, in industrial applications or something like you want to measure, for example, the pressure in a certain region or temperature, magnetic field, rotation, right? Chemical variables like pH or ionic concentration, etc. Right. So there are various sensors, as you know, that can be used to measure these things, right? But actually, using optical fibers devices is actually a very sensitive way to measure these things or small changes in these quantities with high sensitivity, okay, as we will see. So typically, if you nowadays, basically the trend is towards moving towards building photonic devices or like doing measurements using light, because basically you can because of the very precise laser sources and these low loss optical fibers and kind of precise optical devices we can make. Basically, you can change very small changes in the property of light, like phase or intensity or frequency, right? So you can measure these things with very high precision, and basically, if you translate some external environmental factor into changes in these quantities of light, then you can measure small changes. Okay, so basically, one can measure the properties of light very precisely, much more precisely than properties of some other quantities, like, for example, electrical quantities like current or voltage. Right. So basically, optical sensors in general, the current trend has been to move towards optical sensors because they give us more sensitivity, right? And with optical fibers, we have the advantage that, for example, so the sensing mechanism is the light field, right, which is moving through this dielectric medium, optical fibers, right? So, for example, they can be deployed in hazardous areas, right? So, for example, typically electronic sensors fail when you deploy them in sort of regions where the conditions are hazardous, right? But these optical fiber sensors can be used there because the fiber is like a dielectric medium and nothing really, as long as like things are not so bad that the fibers break, you can use them. Also, they are immune to electromagnetic interference, right? So with electronic sensors, any ambient electromagnetic interference then like adds noise to your signal, right? Decreasing your sensitivity. But here, you're immune to all that sort of external noise in the environment, which is of some electromagnetic nature, but the frequencies are very different from the frequencies of light we are using here, so they don't interfere. Okay, so we'll discuss a couple of specific examples for fiber optic sensors. Right, the various different types of sensors used for different types of quantities to be measured, but we'll discuss a couple of them to give you sort of a flavor of how these sensors are built and what is the sensing mechanism. Right? So the first one is this Mach-Zehnder interferometer or interferometric sensor. Right, so you might have already known about, you might already know about Mach-Zehnder interferometers, right? So, for example, in free space, you can build a Mach-Zehnder interferometer, and you can do the same thing with optical fibers. So basically, you have some light source like a laser, right? So for a fiber optic one, you will couple first couple the light into an optical fiber, and then basically you split the light into two. paths, right? So for fiber, you will for example use a 3 dB directional coupler here, right? So now you have 50% of the light coming out in these two arms, right? And one arm is called the sensing arm, the other arm is called the reference arm. Okay, so this is known as the sensing arm, right? So this part or this length of the optical fiber would be exposed to the environment, and so that it is influenced by the quantities that you want to measure, right? So this part of the device will be exposed to the environment. So typically, for example, you coat this this part of the fiber. So basically, typically what is done is you remove the outer plastic covering and the jacket, and you just have the bare fiber with the core and cladding, and then you coat the fiber with some material which responds to changes in the environment, right? So for example, if you want to sense temperature, then you can coat the optical fiber with some material, for example, whose refractive index changes with the temperature, right? So you want to use some material where this change is large, right? Even the bare fiber, like for example, the silica refractive index depends on temperature, right? So you can directly use that also. But if you coat some material whose change is larger, then you can have higher sensitivity, right? So typically you coat that. So right. So two things could happen in this arm. One is basically, as I said, refractive index could change, right? The effective refractive index that the mode C is traveling through this arm could change because of changes in the refractive index of the material, or the length could change slightly. Okay, so for example, if there is some pressure applied on this arm, it could change the length of this arm slightly. Okay. So both these things, the change in the refractive index and the change of length, will change the phase acquired through this path. Okay. The other arm is known as the reference arm, which is basically protected from the environment, right? So this part is sort of sits enclosed within your device, is not exposed to the environment. So this is a fixed arm, right? So the length and refractive index here is constant, right? So the phase acquired through this path is constant, does not change with any external parameters. And then at the output, what you do is, because changes are happening in the phase here, right? And finally, when we detect light on the photodetector, of course, we are measuring intensity, right? So you want to change the phase, or the phase changes here, you want to bring it to intensity. So you have another directional coupler here at the output. Okay, and then you sort of detect the two arms. So you have two detectors here, D1 and D2. Okay, so for example, with change in some external parameter here, the power detected in the detectors D1 and D2 will change. Okay, and by changing the power measure here, we can sort of back calculate depending on the parameters to see what by what amount this external quantity like pressure or temperature or something changed. Okay, so to analyze this type of device, so let's say the power coming here, sending into this port is P0 from the laser. Okay, in terms of the amplitude, it's some amplitude A naught, right? So for example, mod A naught square gives me the power 3 naught. Okay. So now we split it into two. So power in each arm is P naught by 2. Right. So, but in terms of the amplitude, you could, you would naively, for example, first think that the amplitudes are split in the ratio, so 1 over square root of 2, so that mod square, right? So, mod square will give me mod A naught square by 2, so that's P naught by 2, right? But that's not the full story. So, actually, what happens is that there is a phase shift. So, not only, so the amplitudes are equal, but there is a phase shift on one of the arms. Okay, so there is like a phase shift of pi by 2 on one arm with respect to the other. Okay, so that's important to take. So where is that coming from? So go back to our discussion of directional coupler. Okay, so here we have some coupling constant kappa and then some length L, right? So that gives me the splitting ratio. So if we send in light from the two input ports here, A1 in and A2 in as the input amplitudes, then the output amplitudes in the two ports are A1 and A2 out. Okay. So typically, so when we discuss the directional coupler, we typically discuss the case only where we send in the input from one of the ports, right? But in general, I could have inputs from both the ports and also output from both the ports. Okay. So in this case, I would write my output amplitudes, right, as some transformation of the input amplitudes. Right, so this will be a 2 cross 2 matrix, right? So there will be some part which is transmitted, right? So the input from port 1 is transmitted to the port 1 at the output. So there is some fraction there, and there is some fraction of A2, right, which couples over to 1 and comes, right? So basically, I can just like, for example, if you have a beam splitter in free space, right? So there is some, you have some transmission coefficient and some reflection coefficient. Right. So this device is basically like that, right? So you have two input ports, two output ports, just like a beam splitter, right? So effectively, the fraction that goes through here straight through, right? We can write as some transmission coefficient. Okay. So if capital T is the power transmission coefficient, then here I can write this as some square root of capital T because these are amplitudes. So, for example, A1 will be square root of T times, so A1 out will be square root of T times A1 in. So this T will depend on kappa n, right? So, recall they went something like, so cosine squared kappa L will give me the transmission coefficient, sine squared kappa L will give me like how much power is coupled to the other port, right? So, so this has the fraction which is transmitted from here, and then there is a fraction which couples from the other port to here, right? So let's call that as a reflection coefficient, right? So A1 out would be square root of T times A1 in, and then square root of R times A2 in, right? So you would think that, okay, now I can write it like this, but basically if you want to so let us write this as some small t, right? So where t is the amplitude transmission coefficient, right? So we should for example, the magnitude will be the square root of the power transmission coefficient, right? Let's write this as small r and small t. Okay, similarly, A2 out will be R times A1 in, right, and T times A2 in, right. So I can write a 2 cross 2 matrix for this directional coupler here, right, which transforms the input amplitudes into the output amplitudes. Now, again, so first time we would think that, okay, small t is just square root of capital T, and small r is the square root of capital R, where T and R, so T would be cosine square kappa L and R would be sine square kappa L. Okay, but that's not the full story. So basically, in general, these small t and small r would be complex numbers, right? To take into account some phase shifts happening here, right? And basically, one thing that we know from this device is, so this device is lossless, right? There is no loss, which means the total output power should be equal to the total input power, right? So basically, mod of A1 out square plus mod of A2 out square should be equal to mod of A1 in square plus mod of A2 in square. Okay. So this condition has to be satisfied because the total power is the same. Total input power and total output power is equal. There is no loss. Right. So now I can write A1 out and A2 out in terms of A1 in and A2 in. Right. So basically, what is mod A1 square? So this is A1 out conjugate times A1 out. Right. And A1 out I can write as T times A1 in plus R times A2 in. Right. So A1 conjugate will be T conjugate A1 conjugate in plus R conjugate A2 conjugate in. Okay. Similarly for A2. So we plug in for A1 out and A2 out in terms of A1 in and A2 in on this side, right? And this side already we have A1 and A2 in. So from this equation, you'll see that we'll get equations for T and R, right? So basically you can bring this to the other side. So we'll get something, some coefficients of A1 and A2 equal to 0. Okay. So those coefficients have to be 0 because A1 and A2 in general are non-zero. Right? A1 in and A2 in are some arbitrary inputs. And for any input, this equation has to hold true. So basically, so from here you'll get some coefficients time like A1 in square plus some coefficients times A2 in square. Okay, and you also have some cross terms like some coefficients times A1 in A2 conjugate in A1 conjugate in A2 in equal to 0. Right, so basically these coefficients have to be 0, so these coefficients will be in terms of T and R. Right, so just plug this in and write out this equation and find out what these coefficients are. So these coefficients have to be 0 because A1 and A2 are in general some non-zero amplitudes. Right, so from that we get two equations. Okay, so it turns out these coefficients are the same and these coefficients are the same. So we get two equations, this coefficient equal to 0 and this coefficient equal to 0. So from the first one, what you get is basically that mod of T square plus mod of R square equal to 1. Right, so this coefficient is basically something like mod of T square plus mod of R square minus 1. So that is so equal to 0 means the mod of T square plus mod of R square has to be equal to 1. Okay, so that also, so this we should expect already, right? Because we've said that sort of the power is split in the ratios T and R, right? And if the power is conserved, then basically T plus R should be equal to, right? So if we write mod of T square as some capital T, which is the power transmission coefficient, right? So these are the then the power transmitted and reflected from each port should add up to, okay? Again, that is obvious from the lossless condition of the. Okay, so that's one condition. But apart from this sort of obvious condition, you get another condition here from the cross coefficient of the cross term, A1, A2. Okay, so from that second coefficient, what you get is that T times R conjugate plus R times T conjugate should be equal to 0. Okay. So without loss of generality, we can assume. So what matters is basically the relative phase shifts between R and T. Okay. So without loss of generality, we can assume T to be real. So right. So this small t is some real number which is equal to square root of T. Right. And then we can have R in general to be a complex number. Right. But you could also take, for example, R to be real and then allow T to be complex, or you could take T to have some phase and then R will have some particular phase with respect to that. Okay. But all these are physically equivalent. What matters is the relative phase between T and R, right? So, for example, I could multiply this whole thing by some e to the I phi, doesn't matter. Like a global phase is irrelevant, right? Because again, in the end, we measure powers, which is mod square. So this phase is irrelevant. Only the relative phases between R and T are important. So you can see, so if I take T to be real, right, so this I can write as T times R plus R conjugate has to be 0. Right, so if I take R to be as some mod R times e to the I phi, right, that phi is the relative phase between the transmitted and reflected arms. Then from this condition, so you can see basically I'll get 2 times, so I give this like mod T mod R cosine phi, right, so I'll get e to the I phi plus e to the minus I phi, so I'll get a cosine phi equal to 0. Okay, so from the second condition here, you can see that, so for example, for a 50-50 3 dB directional coupler, capital T and capital R are both half, right, 50-50. So mod of T and mod of R are 1 by square root of 2, right? So for this to be 0, basically the angle here has to be pi by 2, right? So if this angle here is pi by 2, so you can see this becomes I times mod of R. Right? Basically, starting from this energy conservation condition for a lossless directional coupler, we get that, of course, the transmission and reflection coefficients should add up to 1, but also that there is a phase shift of pi by 2 between the reflected and transmitted arm. Okay, so basically this matrix I have to write, I can't just substitute square root of T and square root of R for these, but I have to take a factor of I. Right, so I can write this as square root of T, but here I have to take I times square root of R, again I times square root of R and square root of T. Okay, so basically this whole discussion is just to say that these I's have to be taken. Right, so the phase shift is. Right, and so these T and R, as we discussed, so T would be T would be cosine square kappa L and R would be sine square kappa L, right? For the direction coupler, for 50-50, both these will be half 3 dB coupler. Okay, So because of this I, right? So we have a 3 dB direction coupler here. So T and R are half. So if you get 1 by square root of 2, right? So of course the amplitudes get multiplied by 1 by square root of 2. But then in one of the arms you have I phase shift compared to the other. Okay, so that's why. So here if we take A naught by square root of 2, here we have to take I times A naught. Okay, and then so this particular arm here, so let's say it goes through some length here, the sensing arm, so there is some phase shift. So let's first consider the reference arm, so that has some fixed phase shift. So when it enters the second directional coupler here, so now the amplitude is I times E naught by square root 2 coming from here, and then a phase shift e to the I phi 1, which is the phase shift through the reference arm. Okay, and so similarly through the sensing arm, so this becomes A naught by square root of 2 times e to the I phi 2, where phi 2 is phased through the sensing arm. Right? And now for the second directional coupler, again we can use, so now we have this transfer matrix 2 cross 2 for a directional coupler. Right? So we can use the same matrix now, but here now the inputs A1n and A2n are these inputs. Right? So A1n, for example, is A naught by square root of 2 e to the I phi 2, and A2n is I times E naught by square root of 2 e to the I phi. Right? And then using this, now we can find what here. So what the outputs A at D1 and A at D2 would be. And then finally the powers detected, which will be mod square. Right? So A of D1 and A of D2 will come here. So basically, finally you can see we will get A of D1 and A of D2 in terms of A naught, which is the decided by the input power, and this phase shift. Specifically, we'll see the phase difference phi 2 minus phi 1. So basically, if you plug, so these for the input amplitudes here, right, and then AD1, AD2 for the output amplitudes here, we can write right, so we can write A of D1 as 1 by square root of 2, which is square root of t here, times A1 in, which will be this A naught by square root of 2 e to the phi 2. Okay, plus I by square root of 2. So I by square root of 2 times A2, which is this. So here I'll have I times. Okay, so that's my amplitude coming to detected D1. Okay, similarly AD2. Okay, just coming from. So you can simplify these equations a bit. So AD1 you can see comes out to right. So and write this as right. So I take e to the I phi 2 out common. and then so delta phi here is phi 1 minus phi 2, the difference in the phase between the two arms. Right, so then I further take e to the I delta phi by 2 out common. Let's say minus. Right, so if I take e raised by I delta phi by 2 out common from here, so in the brackets I'll get e to the minus I delta phi by 2 minus e to the plus I delta phi by 2. Right, so this basically you can see is sine delta phi by 2. Right, similarly for the second detector, basically we get this e to the I phi 1 plus e to the I phi 2, right, from here. So again I can take e to the I phi 2 common. So I get e to the I delta phi plus 1, and again I take e to the I delta phi by 2 out common. So here I get e to the I delta phi by 2 plus e to the I minus delta phi by 2, right? So here you can see this is cosine delta phi by 2. Right, and finally from the detectors we measure the power, right? So we take mod square. So the power in detector 1, mod of AD1 square, right? So these phases go away, so we get mod of A0 square times sine square. Of this phase difference by 2. Mod of A0 square is basically the input power, right? The input power from here, from the laser. So the power in detector 1 is the input power times sine square of the phase difference by 2, and similarly the other detector you can check basically is P0 cosine squared delta phi by 2. Right, and again P1 by P2 has to be equal to P0 because there are no losses anyway. Right, so you can P1 plus P2 comes out to P0. Right, so as a function of the phase difference between the sensing and reference arms, the power oscillates between the two detectors. Right, so it's P1 and P2. Right, and the phase difference changes basically due to changes in the phase acquired in the sensing arm, right, which is exposed to the environment. So phi 1 is fixed, phi 2 changes, which changes delta. Right, so typically, so you can see that this, so our task finally is to, from the powers P1 or P2, calculate what this delta phi was, and from that delta phi calculate what phi 2 was, and from phi 2 calculate what this external parameter was, what pressure or temperature or whatever we want to sense, right? So basically we want to sense small changes. Okay, so typically for a sensor a linear response is desired, right? So for example, I measure some power change here, some delta P, right? That should be proportional to the change in the physical quantity that I want to measure, right? So some delta temperature or delta pH or delta pressure or whatever, right? So, but this is a non-linear response, you can see, right? But if we operate at this point here, pi by 2, okay, so here basically the response is sort of linear. So the change in the powers in the detectors with the change in phase, small changes in phase, uh, looks roughly linear. Okay. Contrast that, for example, if I am operating at pi, then it's basically the slope is 0. So the change for small changes in phase, the power won't change at all, right? So operating at multiples of pi is actually bad, right? Because for any small change here, the power actually won't change at all. So the best place to operate here is where the slope is maximum, okay, and it looks fairly linear here, which is known as a quadrature point, right? So basically, you operate at a fixed phase difference of pi by 2 between these two arms, right, and look for changes up around pi by 2 due to the external. Right, so basically we are saying this delta phi is pi by 2 under normal circumstances without any external influence, right? So for example, you can do that by having slightly different fiber lengths in these two arms, right? Such that right, the phase difference is pi by 2. Or it could be, I mean, it could be any m pi plus pi by 2 also. It could be anywhere. Right, and then the external environment gives me some small phase change delta. So this is fixed. Okay, so then for example, I can write P1. So for delta phi, I substitute pi by 2 plus this delta. So I get sine square of pi by 4, right? So that's here. So sine square of pi by 4 is basically half plus delta by 2. Okay? And for small delta, right? So basically we want to send some very small changes. So for delta very small compared to let's say pi, right? What we can do is do a Taylor expansion of sine square, right? About x equal to pi by 4, right? And keep only the first order term. Right? Saying that this is small and second and higher order terms will be much smaller. So if you do a Taylor expansion, you just keep the first term, basically you get okay, so now you can see basically the power detected here is linear with the phase change due to the external impact. So for some delta, I'll get some delta P1 here, right? And if I double that change, then the power detected will change in by double amount. Okay. So this linear response, this gives me a linear response, which is basically we want finally from all our sensors. Basically, so then we can just translate directly the amount of change in power to the amount of change in the sense of whatever you want to sense. Okay, so that is done by operating at this coordinate point. Okay, and to now sort of quantify the sensitivity of this sensor. So finally, so we have some power here input, P1 and P2, optical power hitting the detector, right? And now this photo detector converts the optical power into some current. Okay. So some I1 and I2, right, which is proportional to P1 and P2, right? So, so the current here, for example, so if you look at I1, for example, that is some average DC current plus a signal current, which could, for example, be a function of time due to this external stimulus varying with time, right, which you want to monitor. So the current out of a photodetector, so the photodetector basically gives a current which is proportional to the power, optical power. Okay, so this is current in amps. This is the input optical power, let's say in watts. So then there is a constant of proportionality here, which is units you can see is amps per watt. So this is known as responsivity. So rho is some responsivity of the detector, right, which gives me a certain current for a certain amount of optical power. Okay, so from here you can see, so this, for example, is time varying. This is some external stimulus, right? So here I'll have a mean current which is coming from this P0 by 2, which is a DC power, right? And then this actual signal that I get, which is proportional to the external stimulus, right? That is rho P0 by times delta. Okay, so this is a DC current, and then this is some current on top of that, which monitors my external stimulus. Okay. So this is the amount of current that I get out of the detector, right, proportional to my thing that I want to measure. So of course, this detector is not perfect, right? It has some noise. So if the detector was perfect, if it had no noise, then I could measure as small a current as possible, right? So I could measure as small a change in this delta as possible. Any non-zero change I could measure. But there is some noise current also coming out. So basically, if the signal current drops to a level below the noise current, then I cannot measure the signal anymore. So that will give me my sensitivity or the minimum change I can measure. Right? So the noise current typically. So noise in photodetectors is another sort of topic that, for example, we'll discuss in more detail in your optical communications course next semester, right? But for now, we just take the noise current to be a certain value. So if the detector is what is known as short noise limited, okay, so that's the best that a detector can be. So short noise, basically this comes from the discrete nature of the electrons. Right, so current is finally being carried here by individual electrons, okay, and because of the discrete nature of this, it's not like a continuous stream, right? So your individual electrons are coming in bunches, right? And when the next electron arrives, is sort of randomly distributed, okay, and that gives some noise, okay, which is known as short noise. So that amount of noise. And this is fundamental. Again, this coming from the discrete nature of electrons, so from fundamental quantum theory, and there is no, yeah. So basically, this amount of noise has to be there. You cannot avoid that in any detector. So the noise current corresponding to this short noise, okay. So it goes as the electronic charge times the average current that I get out of the photodetector times the bandwidth of detection. Okay, square root of this. right? So the noise current is actually scales with the actual average current coming out of the detector, or square root of that, right? And it scales with the bandwidth of detection, right? So basically, how fast changes I'm able to measure. So if you want to measure fast changes, so delta f is large, so then the noise current will also be large. Okay. On the other hand, if you average for a long time, right? So this bandwidth is basically inverse of the averaging time, right? So if I average for longer, then this delta f goes down and my noise current goes down. So now I'm not sensitive to fast changes because I'm averaging, but then if this external environment is not changing on a fast time scale, then I can average over some time scale to lower this noise current by lowering delta. So E is the electronic charge, 1.6 times 10 to the minus 19. So where this expression comes from, as I said, don't worry about that now. We'll discuss in your course next semester. But right, so this is the average current, and this is basically 1 over T roughly, which is T is the averaging time. Okay, so the minimum signal that I can detect is basically when the signal current becomes equal to the noise current, right? That's the minimum change I can detect, right? So if you look at this current I1 here as a function of time, right? So it has some DC level here, average current, and then it has some fluctuations around. Okay, so I want to know whether this fluctuation is coming from actually a fluctuation in the external environment, or is it just noise, right? So there is some small amount of fluctuation already present without any external stimulus also, which is just the noise current, right? So then the external change here has to be above that, right? And the minimum change I can detect is when basically what is known as the signal to noise ratio. So the signal current divided by the noise current is 1. This is the minimum change I can detect, right? So once the signal current goes below the noise level, I cannot detect it anymore. Right, so the minimum delta here I can detect is when Is is equal to this In. So from there you can see the minimum phase change that is detectable. Okay, comes out to be this. Right? So if I want to change, if I want to detect small changes, basically I need more optical power, right? P0. If I increase P0, that increases my sensitivity. High responsivity of the detector helps, right? And also small delta f. So longer averaging time. Right, so if you take some typical parameters, so for example, an input power of 1 milliwatt, okay, a responsivity of the detector of 0.5 amp per watt, okay, and then let's say an averaging time of 1 second. This means the bandwidth of 1 hertz. Right, so let's assume, so the things we are sensing like temperature and pressure, they vary over slow time scale, so like over seconds, for example. So an average time of 1 second, let's say, is enough such that the quantity here is not changing much within 1 second. So then for these parameters, if you put the numbers here, the minimum phase change that can be detected comes out to be about 10 to the minus 8 radians. Okay, so you can see this is a very small change, right? With some reasonable parameters, 1 milliwatt power, and this is a typical value for the responsibility of the photodetector. So you can see that we can really measure very small phase changes. Okay, so that shows you the power of these optical sensors. Okay, so here we just included the noise in the detector, right? But typically, for example, there will be some noise in your laser also, right? So typically, if you include laser phasor intensity noise also, right? So that's basically saying, so this amplitude here we've taken to be just constant A naught, but it's not constant, right? So there are small fluctuations in the magnitude and also the phase of this A naught, right? So this is also a function of t, and then you have some e to the I phi of t. So these functions of time, right? So basically, if you look at the power, it's like sort of fluctuating a little bit around the average value, right? So every laser has some noise, okay, and you can see that noise will translate into my current noise, because so here P1 and P2 will have some noise coming from P0, right, and that will add to my noise current, right? So if we include laser noise also, then this typically goes up a little bit, but still you can get sensitivity below 10 to the minus 6, right? Even including laser. I mean, nowadays you can even get lasers with very low noise, okay, so that you can operate close to this limit. But even if you take some standard sort of off-the-shelf laser, you can get sensitivities which are at least 10 to the minus 6. Okay, so you can see that yeah, these sensors are quite very sensitive, right? So you can detect very small changes. Right. So from this phase change, finally what we want to do is how much the physical quantity that we want to measure is changing. Okay. So from the current of the detector, we can now calculate how much phase change is happening, and from that phase change, we want to see how much this external quantity that we measure is changing. Okay, so this phase you can see, so it's k k naught times the refractive index, which is so n effective in this fiber mode, times the length, right? So you can see that basically the change in the phase can come from changes in the refractive index or changes in the length, as we discussed, right? So this plus delta n effective times, right? So for example, if I put this delta phi of 10 to the minus 6, right? Typical sensitivity. Let's say we are working at a wavelength 630 nanometer, the typical visible wavelength. Okay, so this n effective will be basically the silica refractive index, right? So around 1.45. Okay, so from here we can get, so a 10 to the minus 6 phase change corresponds to a length change of about 7 times 10 to the minus 14 meter. Okay, so you can see that how sensitive this sensor is, right? It basically can detect changes in the length of fiber in one of the arms by this amount, right? And actually, so you might have, of course, heard about the LIGO detectors, right? The laser interferometric gravitational observatory, so it detects gravitational waves. Basically, the basic idea is just a Mach-Zehnder interferometer, which they do in free space, okay, not in fiber. And of course, some details are complicated, and the interferometer is optimized for a lot of things. These arms are also very long there, right? Kilometer longs. But basically there they are able to detect changes in the path length of 10 to the minus 20, 10 to the minus 18 to 10 to the minus 20 meter. Okay. So basically you can see where optical sensors are going, right, to the levels to which they are going. So now they're used for detecting these gravitational waves, where which give me length changes. So delta L by L they are detect. So the delta L by L that they are detecting is of the order of 10 to the minus 20. Okay, and L there is about kilometers, 4 kilometers. Okay, so you can see that delta L would be like 10 to the minus 16 or something for that. Right, so they're detecting changes in length which is smaller than the size of a nucleus of an atom. Right, so that's how sensitive these detectors can be. Right, that's really remarkable. Even for such a very simple fiber optic Mach-Zehnder sensor like this, we can get sensitivities already. Right, so this is much smaller than an atom. Size of an atom, the Bohr radius. Right, so the fractional change in phase here I can write as the fraction change in length plus the fraction change in the refractive index. Right, so I just divide this by 5 here. Okay, so basically, depending on the particular quantity we want to sense, right? Again, it could be pressure, temperature, pH, whatnot. Right. So that particular change in the quantity could give me a change in the length in the fiber, delta L, or it could give me a change of refractive index that the mode sees, right? Or both. So the contribution of both of these would add up to give me the phase change.